All right, so in this video, we're going to look at integrals with trigonometric functions. And what this is really going to boil down to is just setting up some u substitution with different powers of trigonometric functions combined together. We'll also talk about what we need to do when we can't set up a u substitution, and that'll lead us to the idea of reduction formulas. So that's what we've got on the docket for us in this video. Let's give it a go. So I figured we start off with some small examples just to really see the basics here. We're going to be looking at these integrals. Most of the time they'll have different kinds of functions with powers on them, but let's just start with cosine cubed. And what we're going to do is to try and force a u substitution. Now, the only option that we have right now for u would be cosine of x. And then du is negative sine of x dx. And so you'll notice we need that du, that sine function. So what you could also then notice is that, wait a second, we could split this thing up. And we could call this cosine of x times cosine squared. Actually, I'll put the 2 on this one. Cosine squared of x times cosine of x dx. And then what you could notice is that, well, we can convert this to sines by using the Pythagorean identity. The Pythagorean identity says sine squared of x plus cosine squared of x equals 1. And so what we can notice is that cosine squared of x is equal to 1 minus sine squared of x. So let's just go ahead and swap this out for 1 minus sine squared. Now our integral looks like 1 minus sine squared of x times cosine x dx. And this is actually set up to do a u substitution, but instead of picking cosine for u, we can pick sine of x for u, because the derivative is cosine of x dx right here. And then our integral really just turns into 1 minus u squared du. This is an easy thing to antidifferentiate. The antiderivative of that constant 1 is just u, and then we've got a u cubed over 3 plus our constant of integration. And if u was sine of x, we can call this sine of x minus sine cubed of x over 3 plus c. And we're good to go. So this works out pretty well. For this example, we're going to notice it does not work out well. Notice that if we try and use a Pythagorean identity to convert things back and forth between sines and cosines, we're going to be able to convert this to a 1 minus cosine squared of x function. But that doesn't really help us with a u substitution because we need a single copy of either sine or cosine floating around. Up here, we had this cosine of x that we were able to kind of peel off from our power and turn this odd 3 into an even 2 times a linear piece, right? And so peeling that off was essential for us to get this differential du set up. For us, we're not able to really do that here. So what we can do is use a power reducing formula. This is one that you might know from trig. Oops, this is supposed to be a cosine. Sine squared of x is equal to 1 minus cosine of 2x over 2. Or, if we split this up, this is half minus half cosine 2x. So we can just go ahead and rewrite our integral that way. There's a tiny bit of u substitution here because technically this 2x is composed on the inside, but for the most part, this integral is relatively easy to do. Half x minus, we have a half, oops, there we go, a half sine of 2x, but then with our u substitution, we would have needed another factor of half floating out here, so we'll call that a quarter, plus c. So that's what our antidifferentiation looks like. So again, the big pitfall here is that this even 2 exponent didn't allow us to peel off a copy of a cosine function or a sine function to act as the derivative of u. So that's going to be our general strategy. What we're going to do is just try and use u substitution. We'll flirt around with the Pythagorean identity to see if we can create a power of one trigonometric function multiplied by its derivative. And then when we go ahead and do a u substitution, we just get u raised to some power du. And if we can't do that, we're going to try and take advantage of power-reducing trigonometric identities. The main ones that we're thinking of are sine squared of x equals 1 minus cosine of 2x over 2, or cosine squared x equals 1 plus cosine 2x over 2. I used to never remember which one was which until I read somewhere in a textbook, sinus minus, which is a kind of silly phrase. But it meant sine is the one with the minus here. So sine is minus. Sine is minus. Well, that's kind of silly. We'll also use these Pythagorean identities. Sine squared plus cosine squared equals 1, and then just solve for whatever you need. But what we'll also do is play around with these a little bit more. Well, let me just write these out first. I'll say cosine squared of x is 1 minus sine squared x, and sine squared x is 1 minus cosine squared x. So between these identities, we should be able to get most things set up nicely. Let's take a look at some examples before we move on to talking about other trig functions, and that should go pretty well. While we're doing this, we really should be thinking about some strategy here, right? We want to be able to peel off a copy of one of these trig functions and convert the rest of the powers of those trig functions over to the other one, right? Because we know that if we pick, maybe I'll write this up here, if we pick u equal to sine x, then that means that du equals cosine x. And if we pick u equals cosine x, then that means that du is negative sine x dx. I need my differentials on here. There we go. So we notice that we need to have some extra single exponent, but then when we're doing these conversions with the Pythagorean identities, we need powers that are even. So what that means is that if I tried to write this way, sine to the 7x times cosine cubed x times cosine x dx, and my plan was to take these and convert to sine, that's not going to work out very nicely because I've got this odd exponent. Sure, if I let u be the sine function, that's du right here, but the rest of this isn't looking very good. So what we can do instead is notice that this odd exponent means that I can peel one copy of the sine function off, and I'm left with sine to the 6th times cosine to the 4th. And if I, instead of picking a u function first, essentially say that this is du, then that means my u function is going to be cosine. Now, sure, there's going to be a negative sign, so I'm going to go ahead and throw a negative in here just so that all the signs work out, positive and negatives. But now I can convert this over to cosines. This is really sine cubed squared. Oops, sorry. Sine squared cubed. I wrote that wrong. There we go. And then we can say, all right, I know what sine squared of x is, so this integral really is negative the integral of 1 minus cosine squared of x cubed times cosine to the 4th x times negative sine x dx. And then we've got this stuff here is du. That's u to the 4. That's u squared. So our new integral is 1 minus u squared cubed times u to the 4 du. That should work out pretty well. We can multiply all of this stuff out. It's not nice to do, right? 1 minus u squared cubed is a little annoying. If we know the binomial theorem, then this multiplication isn't hard. But if we don't, then we just have to do a lot of writing by hand. But we can go ahead and multiply all this stuff out, and you're going to notice you're just going to get some polynomial with powers of u. And then we can antidifferentiate that easily, and those will end up being our cosine functions. So I'll let you finish this one out, because I don't think it's that difficult anymore. Let's take a look at another one here. And here we have two odd powers, right? Up here we said, hey, the odd power, that was a nice one to peel off a copy of that function to act as the differential. Let's do the same thing. I might be kind of clever now about how I do it, or at least try and be strategic. Notice that when I had a big even exponent, that was something squared raised to the third power, and multiplying those three terms out, 1 minus u squared times 1 minus u squared times 1 minus u squared, would kind of suck. So what I'm going to do is I'm going to take this one, and I'm going to say, let's make du cosine theta d theta, and that means u is sine theta. That way, I've got sine to the 9th theta times cosine squared theta. I can convert that term times cosine theta d theta. So this is du. This is 1 minus sine squared theta. So that's really 1 minus u squared. So my integral turns out to be u to the 9 times 1 minus u squared du. This is a lot easier to multiply out than if I had taken a copy of the sine function out like I did earlier, and then I'd have sine to the 8th, which is sine squared to the 4th, which is 1 minus cosine squared to the 4th, which would turn out to be 1 minus u squared to the 4th. That would be a huge pain to multiply. So here, I'm kind of picking the lower odd exponent to play with. This multiplication is easy. U to the 9 minus u to the 11 du. Our antidifferentiation is no big deal then. And we can convert back to sines without too much problem. Now, what I want you to notice is that if we had gone back and instead of picking this cosine term to peel a copy off of, and we picked this one, we grabbed a copy of the sine function, brought it to the end, that would change our setup for u, which means at the very end we'd have some big polynomial with u's in it, and we would substitute back into this and have cosines. So there's equivalent answers here. We have these antiderivative families that we can represent in equivalent ways because they're off by just a constant of integration. So in this case, we could go back and do this a little bit differently. Sometimes it's kind of no difference based on which one that you pick. In this one, I think it's strategic to at least make u sine so that we don't have to do lots of multiplication with this big exponent. All right, so what if we can't set up this u substitution nicely? Like in the very first grouping of examples, we had that trig function that was squared, and we had to use a different identity. So what if we don't have any odd exponents for the sine and cosine functions? That's what we're noticing is really a key here, right? Whatever the odd exponent is, that's something that we can play with, grab a differential at the end, convert the rest over to the other trig function using the Pythagorean identity, and do u substitution. So what if we don't have that? Here's an example. So we could go ahead and say, well, the sine squared of x is really 1 minus cosine squared. And so we could say this is cosine squared of x times 1 minus cosine squared of x. That's fine. But what I might do, and it doesn't really matter, what I might do is use those identities that we had earlier that said sine squared of x is equal to 1 minus cosine 2 theta, 2x. I'm mixing up my variables here, over 2. And cosine squared x is equal to 1 plus cosine of 2x over 2. So suddenly, this integral, without doing u substitution yet, turns into 1 plus cosine 2x over 2 times 1 minus cosine 2x over 2. I'm going to factor out a copy of a half from this term and a half from this term. That means I've got a fourth times the integral of 1 plus cosine 2x, 1 minus cosine 2x. I can multiply that stuff out, and I've got a fourth. Oh, I should make that fraction a little cleaner. There we go. A fourth times 1 minus cosine squared 2x dx. Well, I'm still in that same problem here. So now I'll go ahead and I'll do the same thing, except I'm going to change these. I'm going to say, all right, cosine squared of 2x then is 1 plus 2 times that original input. So this is cosine of 4x over 2. So I'll go ahead and put that in place here, and I have a new integral 1/4 times the integral of 1 minus, I'm going to break this up, call it half minus, because I'm subtracting this whole thing, half cosine of 4x dx. 1 minus half is a half. Maybe I could either factor things out or multiply this 1/4 back in place. Let me just multiply the 1/4. A half times a fourth is an eighth. So this is 1/8 minus 1/8 cosine of 4x dx. And finally, I can do a tiny little u substitution. This ends up being 1/8 times x, right? This constant turns into a linear. This is going to turn into a sine function of 4x, but I need to divide by 4, so it's 1/32 plus c. Ugh. So that's kind of annoying. Using these double angle, or sometimes people call them the half angle identities, it's all the same thing, just rearranged. These power reducing trig identities, that can be a little bit tricky to see how that goes. All right, so what about other combinations of trig functions? We're going to specifically just look at tangent and secant, because the cotangent and cosecant functions are going to have the exact same relationships, so there's really nothing to talk about there. So let's talk about first just a couple of antiderivatives that you may have missed on. I expect that a bunch of you guys saw this in Calc 1, but let me just run through this integral again, just so we have an antiderivative of the tangent function. I'm going to call it sine of x over cosine of x. And then suddenly we can say, hey, let's do a u substitution. We can pick our denominator to be u. And then we end up with an integral of 1 over u du with a negative coefficient. That's negative natural log of u plus c. And so we can call this negative natural log of sine of x plus c. Now, you likely haven't seen it written this way. Likely you've seen it written as natural log of secant of x. Oops, I put a sine in here and I want a cosine. I was wondering why that didn't look right. There we go. Plus c. And that's because this is a coefficient of -1. So what we're really doing is saying this cosine of x is raised to an exponent of -1, which means it's 1 over cosine, and that's our secant function. So the antiderivative family of the tangent function looks like natural log of secant. We can do the secant one as well. This one is a little bit trickier to do. You just need to introduce a brand new term. I'm going to write this as secant of x times some funny business. What we're going to multiply on the top and bottom of this is going to seem to just be random and get pulled out of thin air. I'm going to multiply secant x plus tangent x on the top and bottom here. Oh, that's supposed to be an x, and I don't know what the heck that symbol is. There we go. If I do that, when I multiply that on top, I'm going to get a secant squared plus secant of x tangent x. And on the bottom, I have a secant of x plus tangent x. And what you might notice is that conveniently we have this nice pairing, where if we picked the tangent function to be some function, then the derivative of that is secant squared. And secant's derivative is secant tangent. So conveniently, when we do this little trick, we can say u is equal to secant x plus tangent x, and that means du is secant x tangent x plus secant squared x dx. And so our integral turns into just a nice 1 over u du, which is a natural log of u. So we end up with the natural log of secant x plus tangent x. This integral is annoying to memorize, partly because the process is a little weird. You're just pulling a random thing out of thin air, it feels like. Once you get used to the general trick that you're using here, you can kind of reverse engineer it. I know there's a combinations of secants and tangents inside this log, so then you got to just figure out how you combine them. And if you know that you're trying to force this u substitution, then it's not too bad to try and think of what you need to multiply secant by to get the derivative of that thing. Anyways, let's move on. Let's look at the general strategy for integrals involving tangents and secants. And guess what? It's the exact same thing. We're going to still try and force u substitutions. We're going to use trigonometric identities. The only thing that's different now is that for us, if we pick u to be the tangent function, du is secant squared x. Meaning, if we're going to pick u to be tangent, we have to peel off 2 copies of secant. And similarly, if we pick u to be secant x, then du is a combination of secants and tangents. And so we have to be able to peel off 1 copy of tangent and a copy of secant to do this u substitution. Also, if we think about our Pythagorean identity, we can just divide everything here by cosines. And if we do that, we're going to get sine squared x over cosine squared x. And that's going to be tangent squared x. Cosine squared x divided by cosine squared x is 1. And 1 divided by cosine squared of x is secant squared of x. So here's our Pythagorean identity that we'll be able to use. Either secant squared equals tangent squared plus 1, or tangent squared of x is equal to secant squared of x minus 1. So these are the tools that we're going to use. So here are some examples. You'll notice even exponents on both, but that's no big deal. Because remember, if we try and make u to be tangent, we have to pull off an even exponent, and we're going to hope that there's an even exponent left so that we can convert secants over. And if we're going to pick u to be secant, then we have to pull off a single copy of tangent. In this case, if we did that, there'd only be 1 tangent left, and that's not enough to use the Pythagorean identity to convert things over, and a copy of secant. So hopefully we can see here that it's reasonable to set u to be tangent of x, and that means that du is secant squared of x dx. Because what we can do is just rewrite this as tangent squared x times secant squared x times secant squared x dx. These last ones here become du. For this, we'll convert it using this little formula that we've got here. This is going to be tangent squared of x plus 1. And so when we do our u substitution, we're going to have a u squared from this tangent squared, and then we're going to have a u squared plus 1, that's from the secant squared, and then we'll have a du. Doing the distributive property and finishing things out, we end up with u to the 4 plus u squared du, add 1 to our exponents, divide by that number. At this part, we're home free. And then we can convert things back, put our tangents in place. So that doesn't work out too poorly. Let's take a look at this. We're going to switch from both even exponents to both odd exponents. Okay, so in this case now, if we did the exact same strategy and picked u to be the tangent function, we would need to peel off 2 copies of secant, and we'd be left with 3 of them. That's not going to work with using the Pythagorean identity. So let's try the other way around. Let's try picking u to be the secant function and du to be the tangent times secant function. Let me write this nicer. Secant x tan x dx. All right, so that means I need to peel off a copy of secant and tangent. So I'm going to write this as tangent squared times secant to the 4th times secant x tangent x dx, where this last big ugly chunk becomes du. And then I'm going to convert everything over to secants. This is really u to the 4. Tangent squared, we can go up here and remember, well, wait a second, that's just secant squared of x minus 1. So that's going to be u squared minus 1. So our new integral is u squared minus 1 times u to the 4 du, multiply, and I'll let you finish that stuff out. Again, no big deal here because it's just our basic power functions. Our last example that I want to look at is when we have an even exponent on tangent and an odd exponent on the secant function. This is going to end up giving us trouble here Because what you'll notice is that if we pick u to be the secant function, we only need one copy of tangent. And that means we're left with one that we won't be able to convert over to secants nicely. If then we switch and say, well, what if we pick u to be the tangent function? That means du is secant squared, and you can see pretty easily that that's going to be difficult for us to mess around with. So what should we do? This is where we'll end up using reduction formulas. Just like we use those power reducing formulas with sines and cosines, we can do the same type of thing here. I'm going to go ahead and switch this tangent function using our Pythagorean identity. It's secant squared of x minus 1. I'm going to call this oops, I don't need this parenthesis. This is really secant cubed minus secant of x dx. Now we can split this up into two integrals. And this second one, we know. It's the natural log of secant x plus tangent x. This one, though, we need a way to reduce that power. There are some formulas that you can derive in trig classes to do this kind of thing, but I think what we're going to do is just jump right into reduction formulas. These are in our text. They're online. You can Google these. You do not need to have these things memorized. If I ever need you to use them, I'll give them to you. These are beautiful. What this does is it gives us a formula that we can use step by step to reduce the powers of sines and cosines. Also, we can reduce the powers of tangents and secants. So that's really good news. So what you'll notice is that if n is equal to 2 for those first two things, this really just ends up being the double angle and half angle, or whatever you want to call them, identities with some other identities tacked on. For the tangent and secant ones, though, this will be really, really nice. So you can go ahead and look at this secant cubed and say, well, n is equal to 3. So let's just do the integral of secant cubed x dx. Notice this means n is equal to 3. So this is going to be an integral of secant to the n minus 2. Well, if n is 3, then n minus 2 is 1. So that's just, oops, I don't need an integral here. So that's just a regular old secant x tangent x over n minus 1, that's 2, plus 3 minus 2 is 1, and 3 minus 1 is 2, integral of secant x dx. And suddenly, this is an integral that I can solve, right? That's the natural log of secant of x plus tangent of x. We did that earlier in this video. So we can say this is secant x tangent x over 2 plus half natural log secant x plus tangent x plus c. Now, remember, in this case, we would still be subtracting this other natural log, so there's a whole bunch of other combinations that you have to do on here. You'll notice that when n is like 7 or 8 or 9 or something like that, this ends up being a little long to do, but it's not difficult, because whatever integral you're left with here, you can just use a reduction formula on that as well. So you can kind of string these together in this nice little step-by-step algorithm to break this down until we get to either an integral of secant squared, which is tangent, or an integral of secant, which is natural log of secant plus tangent. And all of our other examples are going to work out that way as well. So that's an interesting, nice thing to hopefully see. So really quickly then, we can finish this example out. I think I've got most of this written out already. So we had that this was really an integral of, what did I have it as? Secant cubed minus the integral of secant. So that was, we said, secant of x tangent of x over 2 plus a half integral secant of x. Then we still have, dx. Then we still have this integral right here. I'll leave this one in green. So this was the blue one that we just did. Minus the integral of secant of x dx. So this is really secant x tangent x over 2 minus half natural log secant x plus tangent x plus c. Not too bad. It's a little annoying. I don't expect you to memorize those reduction formulas, but hopefully it's nice to see those. So feel free to look those up. If you need them on a quiz or exam, I'll give them to you. But those are printed in almost every calculus textbook that you would ever see, and they're easily Googleable. So use those. That's all that we've got for this, so hopefully that gives you a pretty good rundown of how to use U substitution on these kinds of integrals to get through all that stuff.